our string looks like this. We are clamping it at both ends. It has a tension, it has a mass density, and it has a length. And we decided its motion is described by the wave equation. d2 y dx2 equals 1 over some velocity squared d2y dt2, where the velocity equals the square root of the tension over the mass density. There we go. The question is, how do we solve this differential equation? And the answer is the same as the other times, is we guess. And now for the wisdom, what do we guess? Well, tricky, tricky. We are going to guess a normal mode solution. There's a reason we've been thinking about normal modes, is they are a good way to describe a string. So in this case, what does a normal mode mean? So y of x and t, for two masses that are coupled, the normal mode meant a case where both masses move at the same frequency. So the way we can guarantee that everything moves at the same frequency is to separate the space and the time parts, right? So we describe the shape as f of x and multiply it by cosine omega t. And that has to be a normal mode. Whatever shape you have, everything has to be moving up and down together at the same frequency omega. So that's our first guess. Y, x, and t equals f of x cosine omega t. And what do you do after you guess? You plug in. So we're going to plug that guess into the wave equation. So if we take two derivatives of that, two partials of that with respect to space, then we know how to take partials. You hold this part constant. It's just a constant. You take two derivatives of f of x. Well, that's just d2f dx2 cosine omega t. We don't know f yet, so we can just say d2f dx2. And that's going to equal 1 over v squared times 2 partials with respect to time. So let's see, the f of x is just going to be along for the ride. Let's see, two derivatives of cosine get you back to negative cosine, but it brings out two omegas. So we have omega squared and then cosine omega t. So that's what happens when we plug in. And, oh, it's negative, so yeah, there's a negative there. Two derivatives of cosine get you back to negative cosine. Okay, so then some stuff cancels. So the cosine omega t goes away. And then we see what the equation told us. We plugged it in. The equation said that is a good guess if d2f dx2 equals minus omega squared over v squared f of x. You say, okay, the equation says, good guess if that's true. And that looks familiar. What is that? That's two derivatives equal negative constant. Oh, that's a simple harmonic oscillator equation again, except it's with respect to space. Right? So f of x obeys the simple harmonic oscillator, or the simple harmonic motion equation of motion. You know what I mean. It's that f of x is sinusoidal. Simple harmonic oscillator equation of motion. So it's sinusoidal. So we'll move on to the next board and think about that guess.